We started the course with the idea of a population with members of a certain size. Let's say capital N is the total number of members. And we had the concept of a random variable, which assigns to each member of the population a number, which is the result of a measurement. Then we moved on to the concept of a histogram, where we took note of the possibility that a particular value of the random variable might be repeated a certain number of times, and these dots here are the members who have that value for this random variable. And then if you redraw that horizontally with the count vertically, otherwise known as the frequency, and the score is the value of the random variable, you get some kind of graph called a histogram, and you can approximate it with a continuous curve. And in any case, if you take the frequency and divide it by the total size of the population, you get a fraction which is either called the proportion or the relative frequency or the probability of that particular value. So that's the basic setup that we had. And so we get to the idea of a probability distribution, which may or may not be bell-shaped, but in any case, horizontally, it's the score, and vertically, it's the probability. And then we took a particular case of this when we considered a binary random variable, which has exactly two possible values, which could be a code for things like black and white, or male and female, or red and green, whatever, any true and false, any kind of double-valued random variable can be encoded as a random variable with the numerical values of 0 and 1. The only thing to ask and answer about such a random variable, called a binomial random variable, is what is the probability of having the value 1. So P equals the probability of 1. Now, if you're talking about coins, you could call it a P coin, and so P is then interpreted as the probability of heads. And if Q stands for the probability of tails, then by the fundamental rule of probability, the sum of all the probabilities has to be equal to 1. So Q would be the probability of tails in a P coin, satisfying this equation. Now, that's not very interesting, but it does get interesting if you take a sample of coins. Let's say, I don't know, N equals 13 coins, an N sample of size 13. And you can ask the question, if you flipped 13 coins, what is the probability of 5 of them being heads? So you have this very general question, what is the probability of K heads in N tosses of a P coin? Hold on a second. Let's just clean that up a little bit. And that's the basic question in the whole chapter on binomial probability. And this involves 3 letters, K, N, and P. And a standard notation for the binomial probability of N coins, which are heads with probability P. The probability of K heads in N tosses of a P coin is given by this intimidating formula, which is N factorial divided by K factorial times N minus K factorial times P raised to the Kth power times Q, or 1 minus P, raised to the N minus K power. And this is the formula that MyStatLab shows you when they do a view and an example, or show me how to do this for a binomial problem. Fortunately, this formula is built into Excel in the function called BINOMIAL.181001a.XLSX. And in alphabetical order, you put in K, N, P, and you put a 0 at the right end, because you're interested in this formula of the exact probability at position K. And the possibilities for K go from 0 to 1 to 2 and so forth up to, well, N. So there's N plus 1 possibilities for K. I'm going to switch over now to Excel to construct this graph accurately and then swing from there into solving problems with an approximation to the binomial distribution, which is actually what happens when you have a very large N, a large number of coins. Things get to be so symmetrical it turns into the normal probability distribution. So that's what I wanted to tell you about. On the left is page 48 of the Cooper textbook that opens with the chapter 6, section 1 on the binary random variable. And what I'm really emphasizing here is at the bottom of the page is what I alluded to in the preceding segment with this formula, with the understanding that this parenthesis with the n and the k and close parenthesis, that's really n factorial over k factorial times n minus k factorial. It's actually pronounced n choose k, which stands for the number of ways that you can choose k items amongst a row of n items, where of course n is bigger than or equal to k, and k is not less than 0. So, for example, n choose 1 is the number of ways to choose one thing in a row of n things, which is n. And if k is n minus 1, interestingly enough, the number of ways you can choose n minus 1 things amongst n things is the same as the number of ways to choose one thing, because choosing n minus 1 of them leaves one of them out. So you can say that's the one you're choosing. Anyhow, we had a little extra credit exercise in class where we actually translated this algebraic formula into Excelish. So I'm going to do that again just for fun. We've got, let's say, a K, an N, and a P. And we'll start with my favorite numbers. N is 13, so we're talking about 13 coins and maybe choosing 5 at a time to see if they come up heads. And we want to know what is the probability of 5 heads in 13 tosses of a P coin. We'll start with a fair coin, so we'll put 0.5 there. And as you know, I like to click on the triangle at the upper left to select the whole sheet and set it to decimal numbers by choosing number in the middle there. And since 2 of these numbers are whole numbers, I'll reduce the number of decimal places there. And so it looks like that. And I'm now going to assign K, N, and P as the names for the cells corresponding to them in the B column. So I go to the Formulas tab, and under Define Names I say Create from Selection, and take the default, choosing the names from the left column. And now these are defined, and I can double check that by pulling down the name box. Well, if I could see the name box, hold on a second. Let's take a look, and here's the name box. K, N, and P are there. Let's go back to screen size over here. And when I've defined names for cells, I like to highlight them in yellow and frame them like that. Okay, so now we can use K, N, and P in a formula. All right, what formula? Well, it's this algebraic expression, n choose k. Frankly, I think there may be a function built into Excel called choose. That would be interesting to see. let me just try that. Equal, choose. Yes. Aha. Okay, so let me uppercase that. Choose. And then it says the index number. Well, that's going to be K, I think. K, comma, N. And let's see what happens here. We don't like that. Well, okay, so how does this work? Value 1. You know what? It's the other way around. You know what? I think it should be N, comma, K. I never did this, so, bear with me. Oh, okay, now we're in trouble. So, you know what? We're going to go look up formulas. Let's say, well, let's make this full screen and fool around with this a little bit. I want formulas and mathematics formulas. Where's choose? You see, it's not exactly here. Oh, combina. Oh, you know what? This is what we really want. Or, you know what? I'm going to do is combine. And I wanted to do that uppercase. But anyhow, N and K. Let's see what that gives. Aha! Now, that's actually familiar to me, so I know I'm on the right track here. All right, so now you're going to say, Dr. Cooper, you got very confused. Why don't you tell me what formula you used? Okay. I select the cell with the formula, go up to the formula bar, select the formula in the formula bar, go Control-C to make a copy in the clipboard, press the Enter key to go down one, up arrow, right arrow, apostrophe, Control-V to paste the formula. And okay, so now you can see the formula that I used. Okay, you like that? So that's the number of combinations of n things taken k at a time. I pronounce that n choose k, but that's just me. But that's a very nice little formula. Let's break that down with factorials. Okay, so here's what I'm saying. I'm going to go like this over here, right underneath to get the same alignment, equal FACT, so I'm going to take the factorial of n and divide it by, now I'm going to be careful with order of operations and put in an open parenthesis, factorial of k, and multiply shift 8 by factorial of n minus k, close paren, close another paren, and this better come out to 1287. Ooh, it does. So you want to see the formula for that. So again, I select the cell with the formula, go to the formula bar, select the formula in the formula bar, Control-C to copy to the clipboard, go down, up one, to the right, apostrophe, Control-V. And now you see kind of a nice thing. We're calculating the same number, the 1,287 ways to choose 5 things among 13, using the built-in COMBIN combinatorial formula, or what it really means, which is n choose k, given in the algebra at the lower left. Okay, very good. But that's not the end of the story, because we want to multiply that value times p to the k times 1 minus p to the n minus k. Okay, so I can do that. I'll tell you what, I'll go like this, equal, and then click on this thing, so I don't have to retype all of that, and multiply by p, shift 6 raised to the k power, and then multiply that, open paren, 1 minus p, close paren, raised to, open paren, n minus k, okay, and that's going to be a probability. Oh, there it is. Let's give it some more decimal places because I'm familiar with this number. So I'll give it some more like this, 0.1571. In other words, let's put the formula up in the formula bar here. And select that, Control-C, down, up, right, apostrophe, Control V. So this says that approximately 16% of the time, if you have 13 coins and you choose 5 at a time, 16% of the time, approximately, 5 will be heads. And that's with a fair coin. P equals 0.5. So here's a question. What if I change P to 0.8? Let's say 0.8. I did not yet press the Enter key because this question came up in class, and we had a little discussion. What do we think is going to happen to that 16% if I raise the probability of heads? Well, let's think this through a little bit. First thing to say is that the total probability for any number of heads, 0 through, well, 13 in this case, the total probability is going to be 1. Now, if I raise the probability of heads, that means a larger number of heads will have a higher probability. But if a larger number of heads has a higher probability, then a smaller number of heads will have a lower probability. So if I raise the probability of heads, the probability of 5 should go down. And okay, it went way down. Now, that's one way to reason through this, and we did talk about that in class. But here's where I get a much better intuition out of this. I'm going to graph the probability distribution for n equals 13 and vary k. So I'm going to make a column for k. I'll make a column for k, call this the k column, and k is going to go from 0 to 13. All right? So I'll start with 0, and there's more than one way to do this. Here's an easy way to do it. I'll start with 0, and I want to increment by 1, so I'll make the first two cells 0 and 1. Now, I don't want so many decimal places, so I will reduce the number of decimal places in this column, but I want it to be centered. I like it to be centered. Okay, so now I have a k column, and I want to extend this list out to 13. So I'll select the two cells that tell Excel the first two numbers in a sequence of numbers, and I go to the lower right-hand corner. And when I drag this down, you see 3, 4, 5, 6, 7, 8, 11, 13, and it fills it in automatically. It gives me the values of k from 0 to 13 automatically. I could have, okay, just for the sake of pedagogy, I could have gone like this. I could have said start with 0, go to 1, but instead of going to 1, I'll go equal to the preceding value plus 1. Now it's going like that. Now I have a formula here. You can see it in the formula bar. And if I go to the lower right-hand corner and copy that formula down, I get the same thing. Okay? Don't want to go into that anymore. Control Z to get out of that. Because now I'm interested in calculating the probability of k heads in n tosses. N is 13, right? Of a p coin. So here's what I'm going to put the fairness back to 0.5. But I'm going to now put in a formula. I'm going to use the formula down here that I said is what calculates this complicated thing that's done in two ways over here. So I'm going to go like this. Equal binom. Let me do uppercase, make it look nice. Binom. Binom.dist, and then, okay, now I need this k to the left here. Click on that, comma n, lowercase, comma n, comma p, and then put a 0 at the right end. I will explain that. We're going to need to understand that real well. So there's the formula. Now you want to know what that formula is. So I'm going to copy it from the formula bar, go down, up, and to the right, put in apostrophe, and okay. So that's the formula in this cell here. Now I want to copy that formula down. So I'll go to the lower right-hand corner here and just go like that. And there we go. There we go. These are the answers. These are the probabilities, the exact probabilities for k varying from 0 to 13. Now, I'm not going to copy this formula down because it's going to keep it at C2, It won't know to make it go from C2 to C3 and so forth. The way this thing goes, as you can see, it automatically knows where it is relative to the value on the left. Okay. Now, even by eyeballing this, you can see, if you look, that for 0, the probability looks like it's 0. It's really not 0. I mean, I can give it a few more decimal places. Okay. It's really not exactly 0. But for 0 and 13, it's the same value. For 1 and 12, it's the same value. For 2 and 11, it's the same value, and so forth. This is symmetrical. But let's graph it, okay? So to do these graphs and make it come out nice, if I just went like this, just watch me get in trouble here, and I say insert, and I say I'm going to insert a bar chart like this one here, I get in trouble. See, it's not exactly in trouble, but what it's doing in blue, it's showing my k values going from 0 to 13, and then it's also got a 14 one there. And in orange down here, if you look carefully, it's showing the probabilities. That is not what we really want to see. We want to see a nice histogram. So I'm going to delete that, and all you do is you put in some word down here. You could put in anything. I could say put in end. I could put in the word more. I could put in the word done. And if I were being really cute, I could even put in a space, I think. Let me just see if that works. I typed a space bar there just for fun. I mean, look, we're in this together, right? Okay, so that works. But you can't read space, so I'll put in the word end and redo that. I hope you can tell what I just did and can duplicate what I just did. And for extra credit, I will ask you to show me that you can do all of this, maybe after class or during in between classes or whatever. Before class, after class. Anyhow, let's insert this beautiful chart now, because it gets real interesting. Get rid of the title. Click on that. Delete that. It just gets in the way. But you can see now we have a really nice probability distribution that's perfectly symmetrical. And it goes from 0 to 13, and then there's the end. Okay. Here's the next fun thing to do. Like I said, if you change the probability P of my P coin to, let's say, 0.8, that means we're going to get a higher probability for a larger number of coins. So when I press enter here, the graph definitely slides to the right. See that? Slides to the right. It's also skewed to the left. It's not symmetrical. Keep that in mind. And as you can see, the probability for 5 heads in 13 tosses of 0.8 coin is now very small. And you can see how big it is right here. It's 0.00108. It's way less than 1%. Okay, very nice. Of course, if I went to the other side, instead of 0.8 for heads, I say 0.2 for heads, which is 0.8 for tails, right? Because P plus Q equals 1. It just shoves it to the left. And for a smaller number of heads, of course, the probability is higher. And so now the probability for a large number of heads is much smaller. It's in one sense, it's symmetrical if I change the probability for heads to equal the probability for tails and back so that they sum up to 1. Okay, that's very nice. I wanted you to see that, but I also want to make some comments about formulas that you will need for the homework for calculating the mean and the standard deviation of a binomial probability distribution. Let me remind you, and I'm not going to do this, with handwriting. I'll just say it out loud, that we had a formula when we had the probabilities for a random variable, and we wanted to calculate the mean. What we did was we multiplied the probability of a value times the value, and then added those all together. Okay? So I'm going to do that right over here. So let me make a a column for this value of the random variable times this probability for it. So I'm going to have, it's going to be an x times a probability of x column. Okay, and we've done problems like this, but now I'm doing it for a binomial where I have all of these nice numbers. So I go, click on the 0 number, Shift 8, get that, and click on the probability for it, and there's the probability for it. That's not a surprise because k is 0 there. But this formula, now I'll drag this down and go like this, and give them some more decimal places. Okay. Very interesting. By the way, for a fair coin, let's make it a fair coin to begin with. This, you get back your symmetrical picture, and these numbers are now symmetrical. What I want to do is add them together, because I said the formula for calculating the mean of a random variable, if you know the probabilities of the distinct values, just multiply the probability times the distinct value and add them all together. So, okay, so I'm going to go equal sum, uppercase sum, open paren, add these together, close paren. And, okay, now let's take a guess here before we do this, because, you see, I'm looking at this graph, and it's perfectly symmetrical, so the mean has to be in the middle, right? So I'll bet you it has to be 6.5. Oh, it is 6.5. Look at that. Very interesting. But let's think about this a little bit more. Suppose I had 1,000 coins, and they're not fair coins. Suppose they're 0.8 coins. So if I have 1,000 coins and they're 0.8 coins, then 80% of the time they're going to be heads. Well, what's 80% of 1,000? Well, it's 800. How did I get that? I multiplied the number of coins, n, times the probability of heads, p times n. And that's the formula I want you to know. Okay, so watch this. I'm going to go, I'm going to make a little formula, p times n. Mean, let's do this nice, okay? So I'm going to say mean equals p times n, and then I'll put an equal sign. This is all text, okay? That's just text. It's not a big deal. But if I double click on this here, I can now justify that, make it look nice. And now I can put in the formula p times n equal p times n. And there's the 6.5. Now I said, I said that if I make n 1,000 and p equal 0.8, I should get 800. So I'm going to do that, but that's going to mess up the graph. Forget about the graph while I do this. I'm just going to put in 1,000 here. The graph goes nuts, and I want to put in a 0.8 here. Oh, there's the 800. Okay, so the mean is the probability of heads times the number of coins. That's an easy formula to remember. Therefore, you are required to remember it. Now, we also had a formula when we were discussing standard deviation, and this came up in homework 3, I think, or 2 even. But let me just remind you, I'm going to say it out loud, that the variance was the sum of the probabilities multiplied times the squared deviations from the mean. Okay? And therefore, the standard deviation is the square root of the sum of the probabilities times the squares of the deviations. But there's a real easy formula for that. I'm not going to go into it right now. You can look it up in the back of the Cooper textbook, and I'll come back to that in a minute, but I want you to know this formula. So I'm going to go STDEV equals, here's the cute little formula. It's P times 1 minus P, which we also call Q, but I want to keep the number of letters as small as possible in this. And that's going to be equal to, over here, equal the square root. Oh, I didn't put in the square root. Hold on. In this thing here, I guess I should have called this variance. Okay, and then we'll take care of it later. Variance. This is for a binomial probability variable. And by the way, I want to right justify that and make it look nice. There we go. Okay, so we go like this. Equal P times, open paren 1 minus P, close paren, times N. And there you go. There is a number. That is the variance of a binomial random variable with probability 0.8. Of course, if I make it 0.5, that would be interesting to see what it is. Fair coin, it's 250. Very interesting. That's very interesting. Again, this is for 1,000 coins. So let's calculate the standard deviation as the square root of that. STDEV is equal to the square root. I don't have a notation for that of the variance, but let's just do it like this. And let's right justify that. And just calculate it, equal SQRT, and then click on the variance up here and get that thing. So now you have it all. I want these to look nice. Oh, that was the wrong thing. I meant this. I don't mean that at all. This is an indent. I don't want any indents. What's this indent thing? I don't know. Oh, I see. That puts it to the left. So if I indent it to the right, no, you can't do that. So let's just go. There you go. That's what I wanted. All right, I'm just fooling around. So let's go back to 13 here, because I want you to see that graph the way it was. But there's an interesting thing. Now that we have these numbers here, we can kind of take a look at how maybe these numbers relate to these numbers here. The standard deviation is 1.8. Okay, so I'll tell you what. Let's go one standard deviation from the mean. Okay, so that means I would be calculating the mean minus the standard deviation. That's going to be equal to what? Well, it's going to be equal to the mean, do an equal sign there, equal the mean number minus the standard deviation number. I'm just curious here and see. 4.7. Now that's very interesting. You see, that's right about over here. Do you understand what I'm saying? I'm looking at the 4. I'm looking at the 5. It said 4.7, so it's right about here. And I don't know if you can tell, but, you know, if you imagine a continuous curve going down, 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 hitting the top edges of these blue bars, it's sort of an S shape, right? It's sort of an S shape. And at the middle of the S shape, where it changes from going one way to going the other way, looks like it's right at that 4.7. Isn't that interesting? Ho, ho, ho. Anyhow, it's actually symmetrical. So I'll tell you what. Let's go to the mean plus the standard deviation. The mean plus the standard deviation. And calculate that over here. Equal the mean plus the standard deviation. What do you think it's going to be? Well, it's going to be 6.5 plus 1.8, so 8 point something or other. 8.3. Well, let's get these things right justified and make it look nice. There you go. Now 8.3. Aha! 8.3. You know, if you imagine an S-shaped continuous curve on the right over here, 8.3 is right where it changes over. Very nice. Okay. So here's what I'm saying. I've just done a almost half an hour YouTube video on basics of binomial random variables in Excel. I just want to show you the mathematics of this. On page 127 of the Cooper textbook, there's the beginning of the explanation of the mathematics behind this factorial formula, the n factorial over n minus k factorial times k factorial. Okay, and so it's a little detailed here with reference to Excel. And this formula that I've been doing about, for example, the mean being p times n is on page 123, and the variance of n times p times q is also on page 123. So you can read these things, and I don't give complete proofs. I do give you references to a fabulous book by Bulmer. It's a classic work, 1979. I think you can get it for a few dollars on Amazon. That is a great little paperback. Okay, I'm